Hello class, welcome to today's lesson. So we have been doing a lot when it comes to differentiation and limit of a function, and today we would like to shift the argument to antiderivative, and the knowledge we acquire from the antiderivative, we'll use it to solve some problems on rectilinear motions, just as we did when we were doing differentiation of a function. So when I came to the class today, I let you divide yourself into groups where one group is having a function and the other is having the derivative. So let's try to go over and see which group was able to do it well. So the first function is that f of s is equal to 1/4 of s exponent 4, and we are to find the derivative. So we can say the derivative of this function, remember what we learned there last time, will be equal to, so we can use the power rule or the scalar multiplier rule to differentiate this function. So we said we drop the exponent to multiply the coefficient, then we repeat one from it. So the differential of this function, f prime of s, will just be, so 4 will divide 4, that will be 1, will just be s exponent 3. Then the differential of the function f of s is equal to sin x, will just be cos s, if you recollect it very well. Then the differential of arctan of x, or tan inverse of s, if you remember very well, we say it is equal to 1 over 1 plus x squared. Then the differential of ln of x, remember absolute value of ln of x, will just be, please, differential. The differential of that will just be 1 over x. Then we also say that the differential sin x, sec s, sorry, the differential of sec s will be equal to sec x tan x, if you recollected very well. So if your group is able to do all, congratulations to you. Today we are going to shift the argument to antiderivative, and the knowledge we get from antiderivative, we'll use it to solve some rectilinear motions as I said. So before the lesson ends today, I expect that we should be able to identify the antiderivative f of s, that's capital F of s, of a function f of x. Then we should also be able to find the general and the particular antiderivative of at least some fundamental functions. Then the knowledge acquired will be able to apply that concept of the antiderivative in solving some rectilinear motion problems that involve position, that's position of an object moving in a straight line, its velocity, as well as its acceleration. So let's get in. You remember when we were doing differentiation, we said that the function is given to us for it to find a derivative. When it comes to antiderivative, the goal of this lesson is that we'll find an unknown function. An unknown function, say capital F of x, if we know its derivative. F of x. So it's just the matter of shifting or reversing the argument in differentiation, where we have the function for us to find the derivative. In this case, we have the derivative and we are going to find the function. So that's it. So we say a function f of s is called an antiderivative of a function. That's a function capital F of s is called as an antiderivative of a function f of s on the interval I if the differential of that supposed antiderivative is equal to what? The function. So it's as simple as that. So if you have a function and differentiate that function, that supposed function you think is the antiderivative, you differentiate it and you get a function, then we say that that function is the antiderivative of the function in question or under discussion. So for instance, we have a function f of s equal to x cubed. So let's presume that the antiderivative of this function, capital F of x, is equal to 1/4 x exponent 4. Now let's differentiate this function. When we differentiate this function, that's capital prime of x, capital F prime of x, that will be equal to, remember we did that here and we had x exponent 3, so we say it's x exponent 3. So you realize that capital F prime of x is equal to f of x. That's the differential of this function is s cubed, which is equal to the function under discussion. Then we can then say capital F of x is an antiderivative. It's an antiderivative of f of x. That's the argument here. We'll look at another example. For instance, we have a function f of s is equal to cos x. And we presume that the antiderivative of this function, capital F of x, is equal to sin x. Now, when we differentiate this function, prime of s, that will give us what? Cos x. The differential of sin x is cos x. So you realize that f prime of x is equal to f of x, and they are both equal to cos x. Then we can then say that capital F of x is an antiderivative. It's an antiderivative of small f of x. So it's as simple as that. So that's it. Now let's take another function. Let's say that the first function which we dealt with, that's f of s equal to s cubed. So f of s is equal to s cubed. Now, I don't want to assume that the antiderivative of this function is just 1 over 4 s exponent 4. I want to say that the antiderivative of this function, capital F of x, is rather 1 over 4 s exponent 4, maybe plus 7. Now, let me differentiate this function and see if the differential of this function, that's the supposed antiderivative, is equal to the function. So let's differentiate that. Capital prime of x will be equal to, when we differentiate this, we get s cubed, remember that. And this is constant. When we differentiate a constant, last we talked about when we differentiate a constant, it's just 0. So we say that capital prime of s, f prime of s, is equal to f of x, even though we added a constant, say 7 to it. The same way, that function, this function, f of s is equal to cos x, let's presume that the antiderivative, capital F of x, is rather equal to cos x, is rather equal to sin x plus maybe 25. So when we differentiate this function, that's capital F prime of x, what are we going to get? When we differentiate sin x, we get cos x. And when we differentiate 2025 is a constant, and that will be 0. So we realize that f prime, capital F prime of x is equal to f of x. Do you understand? So we can then say that the general form of an antiderivative of a function is the antiderivative plus the constant. And that will not change the function. So if f of s is an antiderivative, it's antiderivative of a function f of s on the interval I, then the general form of f of s on I is giving us f, capital F of x, then plus the constant c, where c is constant. C is always constant. So if it is constant, then when we differentiate it, we'll get a function back. So take notice of that. Then we can then conclude that the general form of the antiderivative of f of s equal to s cubed will be written as capital F of s equal to 1 over 4 s exponent 4 plus c. So this will be the general form. And for f of s equal to cos s, it will be capital F of s equal to sin x plus c. I hope you get this argument. Okay, so we'll continue again. Remember when we're doing differentiation, we talk about the power rule, and we say that if we have a function, let's say y equal to s exponent n, and we want to differentiate this function, that's find the dy over dx. The differential of the function is equal to, we said the power rule say we drop the exponent, okay? Then we subtract 1 from it. That's by differentiation. When we come to finding the antiderivative, we are going to reverse the argument. This time around, we'll add 1 to the exponent and divide the function by the result. So we say the power rule of antiderivative of a function f of x equal to x exponent n is giving us capital F of x equal to x exponent n plus 1 over n plus 1. Where, remember, n is never equal to negative 1. Because when n is equal to negative 1, the argument changes, and we are going to look at it later on in this course. So for example, if we are asked to find the derivative of a function f of s equal to s exponent 20. We need not to be guessing, checking, and finding the derivative. We just apply this power rule to evaluate or find the derivative. Then we can say that the antiderivative of this function, that's capital F of s, will be equal to s exponent 20, then plus 1 over 20 plus 1, then plus our constant. So remember, this is plus c, okay, plus the constant which we showed earlier. So then we can say the antiderivative of the function s exponent 20 will just be 20 plus 1 is 21. So that will be s exponent 21 over 21 plus c, which we can rewrite as 1 over 21 s exponent 21 plus c. So realize that when we differentiate this function, we'll get s exponent 20. So we can then conclude that this is an antiderivative of the function s exponent 20. Also, the antiderivative of a function f of x is equal to ax exponent n will be giving us capital F of s equal to ax exponent n plus 1 over n plus 1, then plus our c. So for example, if we have a function f of s is equal to, where the coefficient is not 1, it doesn't matter. We just have to apply the power rule as we are doing. So we can say that antiderivative of this function, that's capital F of s, will just be 5s exponent 9 plus 1 divided by 9 plus 1, then plus our constant, which people call constant of integration. We'll be looking at it later on in this course. Then we have f of s to be equal to 5s, 9 plus 1 is 10 over 10, then plus our constant. So our capital F of s, which is the antiderivative, will be equal to, 5 can go into 10 twice, so that will be 1 over 2 s exponent 10, then plus c. So realize that when we differentiate this function, we'll get 5s exponent 9. So half s exponent 10 plus c plus any constant is the antiderivative of the function f of s equal to 5s exponent 9. Let's look at more examples. So for example, if I have a function f of s equal to 6 and we are asked to find the antiderivative, f of x can still, f of s equal to 6, we can rewrite this as 6x exponent 0, because any number exponent 0 is 1 from our laws of indices or from identities of indices. So in finding the antiderivative of this function using the power rule, we say capital F of x will be equal to 6x exponent 0 plus 1 over 0 plus 1, then plus our constant. So we say f of s will be equal to 6. So 0 plus 1 is 1, and that will s exponent 1 will just be x. 0 plus 1 is 1, divided by that will just be 6s, then plus our constant. So we can therefore conclude that if a function f of s is equal to, let's say, constant c, then its antiderivative, or let me use a different number, a different constant, say a, then its antiderivative f of capital F of s will just be ax, then plus our constant. I hope you get this. Also, the antiderivative of a function, that's the sum of two functions, f of x plus g of s, is giving us the antiderivative of each of them, the sum of the antiderivative of each of them. That's capital F of s plus capital G of x. I hope you get that. So we are going to use that concept. If you are asked to find the antiderivative of a particular function, you will just find the antiderivative of each term. That's all. So for example, if we have f of s equal to this function and we are asked to find the antiderivative, we can say the antiderivative capital F of x will be equal to 5s exponent 4, so plus 1 over 4 plus 1, plus 4s exponent 3 plus 1 over 3 plus 1, minus 3s exponent 2 plus 1 over 2 plus 1, then plus 2s, remember this is exponent 1, so 1 plus 1 over 1 plus 1, then minus 3, remember this will be 3s exponent 0, so 3s exponent 0 plus 1 over 0 plus 1, then of course plus our constant. So capital F of s will just be equal to 4 plus 1 is 5, so we have 5s exponent 5 over 5 plus 4s exponent 3 over 3 minus 3s exponent 3. So 3 plus 1 is 4, so that will be 4s exponent 4 over 4. Sorry for that. Then this will be minus 3s exponent 3 over 3, then plus 2s exponent 2 over 2 minus 3x exponent 1 over 1, then plus our constant. When we polish this further, the antiderivative of that function will be 5 divided by 5 is 1. So we have s exponent 5, then plus 4 divided by 4 is 1, so plus s exponent 4 minus 3 divided by 3 is 1, so s exponent 3 plus 2 divided by 2 is 1, so s square, then minus 3x, then plus c. So you realize that when we differentiate this function, we are going to get the function back. I hope you get that. This is very interesting. Okay. Now let's try to do more example. For example, they say find all function f of s such that f prime prime of s is equal to s cubed plus 2s minus 2. That's the second differential of a particular function. The second differential of a particular function is this, and we are asked to find the one particular form of the function. So we can say when we find the antiderivative of the second differential of a function, we get the first differential of the function. Then when we find the antiderivative of that first differential, then we'll get a function back. So first, we know f prime prime of x is equal to x cubed plus 2x squared minus 2. Then we can say f prime of x will be equal to s exponent 3 plus 1 over 3 plus 2s exponent 2 plus 1 over 2, that's 2 plus 1 is 2, then minus 2s exponent 0 plus 1 over 0 plus 1, then plus our constant. So our f prime of x will be equal to 1/3 s, so 3 plus 1 will be 4, sorry, so that will be 1/4 s exponent 4 plus 2 divided by 2 will be 1, so plus s exponent 2 plus 1 is also 3, sorry, 2 plus 1 is also 3. So we have 2 over 3 s exponent 3, then minus 2x plus c. This is the first differential of the function. So we differentiate this function again. We find the antiderivative of this function again to get the antiderivative or the function that we are looking for. So this will be capital F of s will be equal to 1/4 s exponent 4 plus 1 over 4 plus 1 is 5. Then plus 2/3 s exponent 3 plus 1. 3 plus 1 is 4 minus 2s exponent 1 plus 1. 1 plus 1 is 2. Then plus, remember, we said that when we are finding the antiderivative of a constant, is just the attachment. Then plus our constant. So we can then conclude that the antiderivative of this function, that's capital F of s, will be equal to, so 1 over 4 s exponent 5 divided by 5, then plus 2/3 s exponent 4 divided by 4 minus, this will give us 1, so s squared plus cx, then plus d. So when we polish that further, 1/4 divided by 5 will give us 1 over 20 s exponent 5 plus 2/3 divided by 4. That will give us 2 over 12 s exponent 4 minus x squared plus cx plus d. So when we move further, we polish this further, our f of the antiderivative will be 1 over 20 s exponent 5 plus, this will be 1 over 6 s exponent 4 minus x squared plus cx, then plus d. So when we differentiate this function, we'll get this back. Or when we differentiate this function twice, we'll get this back. Then we can conclude that this actually is the function whose second differential is written as this. So if a particular value at when a function at a particular value is given to us, we can then find a particular function to our function whose differential is given. So instead of having the constant c, we'll have that particular value. For example, they say given that the derivative of a particular function is given as this, find the function if f of 1 is 0. So first, the function f of x is given as 5s exponent 4 plus 1 over s exponent 4. We can rewrite this as 5s exponent 4 plus s exponent negative 4 using indices. Then the antiderivative of this function, I know you get to know this by now, will just be 5s exponent 5, that's 4 plus 1, divided by 5, then plus s exponent negative 4 plus 1, divided by negative 4 plus 1. Then plus our constant. So f of s, capital F of s, will be s exponent 5, then negative 4 plus 1, that will give us negative 3, so over negative 3, then plus c. When we polish this further, we can get s exponent 5 minus 1 over 3 s exponent 3 using indices, then plus our constant. So if we substitute 1 into this function, the answer should be equal to 0. Then we can say that our f of 1 will be equal to 1 exponent 5 minus 1 over 3 times 1 exponent 3, then plus c should be equal to 0. So we have 1 minus 1 exponent 5 is 1 over 1 exponent 3 is 1. So we have 1/3 plus c, that will be 0. 1 minus 1/3, that will be 2/3, plus c, that will be 0, and c will be equal to negative 2/3. Then we can say that particular function whose derivative is given as this will be equal to s exponent 5 minus 1 over 3s exponent 3, then minus 2/3, because c is equal to 2/3. So we are going to look at other forms of antiderivative that does not necessarily involve the power rule. So for instance, remember when we're doing the power rule, we said that n is never equal to negative 1. So this f of s is equal to s exponent negative 1. When you try to apply the power rule, negative 1 plus 1, that will give you s exponent 0. So we don't usually, you can't use the power rule when the exponent is -1. But remember that we said that if we differentiate a particular function and we get a function under discussion, then that particular function is the antiderivative of the function. So when we differentiate, that's ln absolute value of x, the answer will be 1 over x. Remember when we're doing derivative. Then we can say that f of x equal to ln absolute value of x is the antiderivative of 1 over x. The same way, you remember when we differentiate e exponent x, we'll get e exponent s in our last discussion. Then we can say that e exponent s is the antiderivative of e exponent x. Also, remember when we differentiate sine x, we'll get cos x. Then we can say that sine x is the antiderivative of cos x. Or in the other argument, what we'll be looking at it, when we integrate cos x, we'll get sine x. So we'll be looking at that later in the course. Also, the differential of the function negative cos x will give you sine x. Then we can say that negative cos x is the antiderivative of sine x. Or in other vein, people will say that the integral of sine x is negative cos x. That's it. Let's look at some more. The same argument here too. Remember, when we differentiate tan x, we are going to get sec square x. Then we say that tan x is the antiderivative of sec square x. Also, when we differentiate sec x, we'll get sec s tan x. Then we can say that sec s is the antiderivative of sec s tan x. The same way, you remember when we differentiate arctan of x, we'll get 1 over 1 plus s squared. Then we can say arctan of s is the antiderivative of 1 over 1 plus s. Later on in this course, we are going to prove the reason why it's like that. But now we are just looking at the general form or other antiderivatives. The same way too, when we differentiate arc sine of x or sine inverse of x, we'll get 1 over the square root of 1 minus x. Then we can say arc sine of x is the antiderivative of 1 over square root of 1 minus x. When we come to that, we generalize the argument into hyperbolic functions. We say that when we differentiate hyperbolic sine, that's sin x, we get cos s. Then sin x is the antiderivative of cos s. The same way, when we differentiate cos s, we'll get sin x. Then we can say cos s is the antiderivative of sin x. The same way, if we have b exponent x over ln b, when we differentiate this function, we'll get b exponent s. Then we can say b exponent s over ln b is the antiderivative of b exponent x. Okay, so let's try to apply this other form of antiderivative to solve some problems. So we say find the most general antiderivative of the following function. F of x equal to 4 sin x plus s exponent 5 minus root of s all over x. So we can rewrite this function as 4 sin x, then plus 2s exponent 5 over x minus s exponent half over x. Then when we rewrite this, we'll get 4 sin x plus 2s exponent 4. Then when we apply indices, this is exponent 1. When two indices are divided with the same base, we just subtract the exponent. So we have minus s exponent negative half. That's half minus 1. Then when we try to find the antiderivative of this function, term after term, that's capital F of x, that will be equal to, we said that the antiderivative of sin x, is negative cos s. So we can say this will be 4 bracket negative cos x. Then plus we apply the power rule here. So this will be 2s exponent 5 over 5. That's adding 1 to the exponent and dividing the function by the result. Then minus the same way we apply the power rule here. Negative half plus 1 over negative half plus 1. Then plus our constant. So when we rewrite this very well, we'll get negative 4 cos x plus 2/5 s exponent 5. Then this will give us s exponent half, positive half, over half, then plus c, which we can rewrite as negative 4 cos x plus 2/5 s exponent 5. Then 1 divided by half is 2, so we have minus 2 s exponent half plus c, which we can rewrite further to be negative 4 cos x plus 2/5 s exponent 5 minus 2 root of x plus c. So you realize when we differentiate this function, we'll get this back. Then we can say this is the general form of the antiderivative of this function. The same way, let's further go and find the antiderivative of this function. So we say that the antiderivative of this function 10 by 10. Remember, we said the antiderivative of cos x. From here, we said the antiderivative of cos x is sin x. So we can say that this will be sin x, and the antiderivative of sin x is cos s. Cos s. Then plus our constant. So the antiderivative of this function is this. That's the general form. Let's go further to look at another example. So this function can be rewritten as 5 over s exponent 6 minus 4s exponent 3 over s exponent 6 plus 2s exponent 6 over s exponent 6. Then we can rewrite it again as, using indices, 5s exponent negative 6 minus, this will give us 4x exponent negative 3, 6 minus 3 minus 6, then plus 2. Then we can now differentiate, find the antiderivative of this using the power rule. So we have 5s exponent negative 6 plus 1. Negative 6 plus 1 will give us negative 5 minus 4s exponent negative 3 plus 1. Negative 3 plus 1 will give us negative 2. Then plus 2s. Remember, this is exponent 0, so 0 plus 1 over 1. 0 plus 1 is 1, then plus our constant. I'll rewrite it very well. 5 divided by negative 5 will be negative 1, so minus s exponent negative 5. Then this will be plus 2 s exponent negative 2, then plus 2x, then plus c, which we can rewrite very well as negative 1 over s exponent 5 plus 2 over s squared, just using indices, plus 2s, then plus c. Then we can say this is the antiderivative of this function. Also, let's look at this. So this one, we have to apply our knowledge about polynomial division before we can be able to solve it well. So this will be our dividend. Then we have the divisor. Then we try to use it to divide. We can rewrite it properly. So let's write this in terms of decreasing power. So we have x squared plus 2, then x squared plus 1. So x squared will divide x squared once. X squared times 1 will be x squared. 1 times 1 will give us 1. When we subtract, we'll just get 1. Then we can therefore say that our f of s can be written as, remember, we said that when we divide, this thing will be quotient plus the remainder is 1, plus the remainder over the divisor. So now we can find the antiderivative. So the antiderivative of this function, so this is a constant, the antiderivative will just be what? will just be x. I hope you get that. Then this 1 over x squared plus 1 is looking like this, right? So the antiderivative will be what? Arctan x. So we can say plus arctan x, then plus our constant. Then this becomes the antiderivative of this particular function. So let's solve some more examples again. So this one is if the differential of a function or the derivative of a function is given as this, and f of 0 is -2, we should find the function. So we just find the antiderivatives. First of all, we can rewrite this function as e exponent x plus 20 over 1 plus x squared using indices. So the antiderivative of this function, the antiderivative of e exponent s is just e exponent x. Then the antiderivative of this, we can rewrite this as 1 over 20 times 1 over 1 plus x squared. And that the antiderivative of 1 over 1 plus x squared is just arctan of x, then plus our constant. Now we substitute 0 and equate it to 2 to find our constant. Now we substitute 0 and equate it to -2. So we say our f of 0 will be equal to e exponent 0 plus 20 arctan 0, arctan of 0 plus c equal to -2. E exponent 0 is 1, arctan 0 is 0 times 20 will be 0, then plus c will be equal to -2, c will be equal to -2 minus 1, c will be equal to -3. So we have our f of s, that's the antiderivative, a particular antiderivative will be e exponent x plus 20 arctan x, then minus 3, which is the constant c. So, okay, so there's another example. They say if the second differential of a function is given as this, and f of 0 is 4 and f of 1 is 1, we should find the antiderivative, or we should find the function actually. So remember, when we find the antiderivative of this function, we have the first differential. So this will be 12s exponent 3 over 3. I know you'll be okay with it by now. 6s. So we can have 6s square over 2, then minus 4s, then plus our constant. When we polish this further, we'll get 4s squared plus 3x squared minus 4s, then plus c. We differentiate this again. So we differentiate this again. We have, is that okay? So when we find the antiderivative of this, then we'll get a function. So we have, this will be 4s exponent 4 over 4 plus 3s exponent 3 over 3 minus 4s square over 2, then plus cx. Remember, this is constant. Then plus the constant, another constant d. So we have f of x to be equal to, so this will give us s exponent 4 plus s exponent 3 minus 2s squared plus cx, then plus d. Now we'll find f of 0. F of 0 will just be 0 exponent 4 is 0. So this will be 0 plus 0 minus 0 plus 0 plus d, and that should be equal to 4. So we can then conclude that d is equal to 4. Also, f of 1 is equal to 1. So we can say when we substitute 1 here, our f of 1 will be 1 exponent 4 plus 1 exponent 3 minus 2 times 1 square plus c times 1 plus d, and that should be equal to 1. So 1 exponent 4 is 1 plus 1 minus 2 plus c, and our d is 4, so plus 4 will be equal to 1. 1 plus 1 is 2, minus 2 is 0, so we just have c plus 4 equal to 1, and c will be equal to -3. So our function, which we are looking for, will be f of s, which is equal to s exponent 4 plus s exponent 3 minus 2x squared c is what? Negative 3, so minus 3x, then d is 4, so plus 4. So you realize that when you differentiate this function twice, you get this. That's very interesting. Let's solve another example. They say if the f double prime of t is equal to e exponent t plus 3 sine t, we should find that particular function whose second derivative is given these conditions. So when we find the antiderivative of the second differential of a function, we'll get the first differential. So this will be equal to 2. The antiderivative of e exponent t is just e exponent t, then plus the antiderivative of sine t, remember, is negative what? Cos t. You remember that. So we said this will be 3 times negative cos t, then plus c. We can rewrite this very well as 2e exponent t minus 3 cos t, then plus c. Now we'll find the antiderivative again of this function to get a function back. So our f of t now will be equal to the antiderivative of this still will just be e exponent t minus 3. The antiderivative of cos t is sine t, then plus the antiderivative of a constant is the attachment of the function. We look at it, then plus our constant. So our f of t will be equal to 2e exponent t minus 3 sine t plus ct plus d. Now we find f of 0. Our f of 0 will be equal to 2e exponent 0 minus 3 sine 0 plus c times 0 plus d, and that should be equal to 0. E exponent 0 is 1, so we have 2. Sine 0 is 0, so we have c times 0 is also 0, then plus d will be equal to 0. So our d will be equal to negative 2. Now we find f of pi, that will be 0. So we say f of pi will be equal to 2e exponent pi minus 3 sine pi plus c pi plus d is equal to 0. So we have 2e exponent pi. Sine pi is 0 times 3 will be 0. So plus c pi. Remember d is minus 2 and that will be equal to 0. So we can say c pi is equal to 2 minus 2e exponent pi. Then our c will be equal to 2 minus 2e exponent pi all over pi. Then when we substitute that into this function, into our function here, then we say that that particular function f of t will be equal to 2e exponent t minus 3 sine t. Then our c is what? Is this. So we say plus. Then c is 2 minus 2e exponent pi over pi, then times t, that's the t attached to it, then plus d, and that d is negative 2, so minus 2. Let's rewrite it here very well. Our f of t will be equal to 2e exponent t minus 3 sine t plus 2 minus 2e exponent pi all over pi t minus 2. Then this becomes the antiderivative of the second differential of that particular function. So now, having acquired this understanding of antiderivative, we are going to use that to solve problems involving rectilinear motions. That's the movement of an object in a straight line. Remember, when we're doing derivative, we apply that in finding the derivative in finding problems involving rectilinear motion. And we said that the derivative of the position, that's s of t, with respect to time, of an object is its velocity. Thus s prime of t will give us v of t. Also, we also said that the derivative of the velocity, f of t of an object is its acceleration. Thus, v prime of t is equal to a of t. So now when we are talking about antiderivative, we are going to reverse the process. Now, when we don't know the velocity or we don't know the position of the object and we know the acceleration, we must reverse back to the velocity, then to the position using an antiderivative. For the motion of an object moving in a straight line, its position s of t is the antiderivative of its velocity. Then its velocity, v of t, is the antiderivative of its acceleration. I hope you get that. So we are just reversing the process now when we're doing derivatives. So now let's apply that in solving some problem. So they say a particle moves in a straight line and has an acceleration given by a of t equal to 6t plus 4. Its initial velocity is v of 0 equal to negative c. That's the particle is retarding at time equal to 0. And its initial displacement s of 0 is 9 meters. We should find the position of the particle at time t. So having known the acceleration of the particle to be 6t plus 4, we just find the antiderivative of this particle to and that becomes the velocity. So the velocity of this particle will be equal to, so the antiderivative will be 6t squared over 2, then plus 4t, then plus our constant. V of t then will be equal to 3t squared plus 4t, then plus c. So this is the velocity. We need the position, so we differentiate, we find the antiderivative again. So the antiderivative of this will just be 3t cubed over 3 plus 4t squared over 2 plus ct, then plus another constant, say d. So our s of t would then be t cubed plus 2t squared plus ct plus d. And he said that the velocity of the particle at time 0 is negative 6. That means when we substitute 0 here, v of 0, we should get negative 6. V of 0 then will be 3 times 0 squared plus 4 times 0 plus c. That will be equal to negative 6. And c will be equal to negative 6. So we can say our s of t is equal to t cubed plus 2t squared minus 6t plus d. And s of 0 is 9. So we say s of 0 will be equal to 0 cubed will be 0 plus 0 minus 6 times 0 will be 0 plus d, and that should give us 9. Then we can say d is equal to 9. Then that position of the object at time t will be equal to t exponent 3 plus 2t squared minus 6t. Remember, c is 6, negative 6, then plus d, which is what? 9. So that's it. So when time is given to us at any particular time, or when t is given to us, that's at a particular time, we'll be able to find the position of the object. Let's solve one more example. It says find the position of a particle if its acceleration t squared minus 4t plus c, given that s of 0 is 0 and s of 1 is also equal to 20. So we know the acceleration of the particle to be t squared minus 4t plus 6. When we find the antiderivative of this, we'll get the velocity, right? So this will be 1/3 t cubed minus 2t squared plus 6t, then plus our constant. Now we need a position. So we'll find the antiderivative again. S of t will be equal to 1/3 t exponent 4 over 4 minus 2t exponent 3 over 3 plus 6t squared over 2 plus ct, then plus our constant d. So I'll polish this further. The position of the object will be equal to 1 over 12 t exponent 4 minus 2/3 t cubed plus 3t squared plus ct plus d. Now the position of the particle at time 0 is 0, so we substitute that. S of 0 will just be, this will be 0 minus 0 plus 0 plus 0 plus d, so d, and that should be equal to 0. So we can say d is 0. And s of 1 is 20. So we have 1 over 12 times 1 exponent 4 minus 2 over 3 times 1 cube plus 3 times 1 square plus c times 1 plus d, that should be equal to 20. So this will be 1 over 12 minus 2/3 plus 3 plus c. Remember d is 0, so that will be equal to 20. So when we solve this, we'll get 29 over 12 plus c, and that should give us 20. C will be equal to 20 minus 29 over 12, and c will be equal to 211 over 12. Then we can say the position of the particle at any point in time t will be 112 t exponent 4 minus 2/3 t exponent 3 plus 3t squared, then plus 211 over 12 t. I hope you get that. So today, generally what we have been learning is the antiderivative and how to apply the antiderivative in solving some rectilinear problems. So we said that if a function f of s is called an antiderivative of, that's capital F of s is called an antiderivative of f of s on the interval I, then it means that the differential of that function is equal to the function under discussion. And also we said the most general form of antiderivative of a function f of s is given as capital F of s plus our constant. And we said we also learn how to find the antiderivative for some different functions, which we look at it with a lot of examples. Then, of course, we apply the antiderivative in solving some problems involving rectilinear motions. So we end it here today. Try to do your assignment until we meet again. Bye-bye.